Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover part 2 of variation of parameters, really just a second example. Now I've chosen this example because the f of x that we're equal to is outside of maybe common families that you're accustomed to using other methods, like maybe the sine of x or the cosine of x or e to the x or polynomial. In this case, it's equal to the tangent of x, and this is really one where maybe a variation of parameters would shine over the other methods. So first we have to find our complementary solution, so we can find our y1 and our y2, and that'll help us build the matrices and then of course the determinants to be able to use Cramer's rule to find the other solutions. So we know that looking at the complementary solution, which is where this is equal to 0, we're going to have our r squared plus 1 is equal to 0, using the characteristic equation, and this is going to give us r, which is equal to r squared is equal to -1, so r is going to be equal to 0 plus or minus 1i. So we know that the solution to this is going to be the complementary solution is going to be e to the 0x times c1 cosine of 1x plus c2 sine of 1x, where the 0 comes from the real part, and these 1's come from the imaginary part of this complex root. So then we know that the complementary solution is just going to be equal to c1 cosine of x plus c2 sine of x, which then is going to make our y1 the cosine function and our y2 the sine function. So our y1 is going to be equal to the cosine of x, and then our y2 is going to be equal to our sine of x. Now, when we set up our determinants, we know that w is going to be equal to the determinant of y1, y2, and this is going to be y1 prime, y2 prime. That thing's determinant. W1 is going to be the determinant of, remember that we're going to replace, it's going to be 0 and then the tangent, or f of x. So this is going to be in the first column. So this is going to be 0. This is going to be f of x. And over here we're going to have y2 and then y2 prime. And then finally w2, we replace the right column with your 0 and the f of x. And then your left column is going to be, y1, y1 prime. So very similar to Cramer's rule. So now when we set these things up, I'm going to need to know what is, y1 prime. Well, this is minus the sine of x. And then what is y2 prime? Well, this is going to be equal to the cosine of x. So then finishing this off, this w is going to be equal to y1, which is your cosine of x, y2, which is going to be your sine of x, y1 prime is minus the sine of x, and y2 prime is going to be equal to the cosine of x. It's funny, as you might ask, would it matter if these were in different orders? And no, I would recommend you give it a shot yourself and see if it matters if you rename this y2 and this one y1. But in general, we go this way. So this is this w1 is going to be equal to 0, and then f of x is going to be our tangent of x, and our y2 is going to be equal to the sine of x, and this is going to be equal to the cosine of x, and then our w2, this determinant, is going to be equal to y1. So we have cosine of x minus sine of x, and then we're going to have 0, and then f of x, which is going to be the tangent of x. So, finishing this off, it's going to be cosine times cosine, which is going to give us cosine squared of x, minus, this is going to be sine times negative sine, so minus sine squared of x. We can see that this cosine squared of x plus sine squared of x, so this is nothing more than 1. Now over here we're going to have 0 times cosine, so we're going to have 0, and then minus sine times tangent, sine of x times tangent of x. So this is negative sine of x times tangent of x. And then our W2 is going to be equal to cosine of x times tangent of x, minus 0 times sine of x, so it's going to be that. Now, U1 prime. This is 1. So U1 prime is going to be equal to, it's W1 over W, so this is W1 over W. So W1 being this thing, W being just 1. So this is going to just be, minus the sine of x times tangent of x, over 1. And then U2 prime is going to be, we know that it's W2 over W, W2 being right here, and then W being 1. So this is going to be the cosine of x times the tangent of x. And, times, we'll divide it by 1. Now, in order for us to find, remember the way our solution is we need U1 and U2, not U1 prime and U2 prime. So I'm going to have to take the antiderivative of these things. So U1 is going to be equal to the antiderivative of minus the sine of x, tangent of x, dx, which we know that this is going to be, this is sine over cosine. So, pulling out that negative, this is going to be the integral of the sine squared of x over the cosine of x dx. And there's multiple methods. I think maybe the one I like here is going to be equal to turning the sine squared into 1 minus cosine squared. So 1 minus cosine squared of x all over cosine of x. So when we split this, this is now going to be minus the integral of 1 over the cosine, which is the secant of x. And I know that thing's antiderivative. I know it's that messy logarithm. And then minus, this is going to be cosine squared of x over cosine of x, which is just going to be our cosine of x dx. So this is going to be equal to, the natural log of the secant of x plus tangent of x. That's the antiderivative of this. Oh, I forgot my negative sign. Minus this entire thing. And then the antiderivative of the cosine of x is going to be equal to the sine of x. So this would be, minus the sine of x. Now I'm going to distribute this negative through. So it'll make the first term negative, make the second term positive. Okay. Boop. All right. So next we need U2. Well, U2 is going to be equal to the antiderivative of, U2 prime. So this is going to be the, the cosine of x times the tangent of x dx. Now the tangent is sine over cosine, so we can see that the cosines cancel. So this is just the integral of the sine of x dx, which is going to be equal to minus cosine of x. So we are so very close, but also, oh man, it's so very much out of room. I will squish it in against my better judgment so we can leave everything in here. So I will pre-apologize for me squishing it into the corner. Now remember that the particular solution is equal to, u1y1 plus u2y2, and we know y1 and y2. We also know u1 and u2. So y sub p is going to be equal to u1, which is this thing. So the natural log of the secant of x plus the tangent of x plus the sine of x. Now remember, this is all times our y1, which is going to be the cosine of x, plus our u2, y2, at least u2 is going to be small, so minus the cosine of x times, small expression, times y2, which is going to be equal to the sine of x. And what I'm seeing here is it looks like when I distribute this, I'm going to get a sine of x cosine of x, and I have the opposite of sine of x cosine of x. So really what it looks like, we're just going to have the cosine of x times this piece right here. And is that what I have? Not what I wrote, but that's what I'm seeing. So this is going to be equal to, you know, again, these will cancel when I distribute with these, but then this cosine still has to multiply by this. So by this logarithm, so the logarithm of the secant of x plus the tangent of x. Okay, now remember that, oh my gosh, I'm out of room. I'm going to go back up here. So this is our y sub p. Remember that our real solution, or not a real solution, but our full solution, which I will write underneath this thing, is equal to y is equal to the complementary solution plus our particular solution. So, you know, our complementary solution being, well, was these. It was c1 cosine of x plus c2 sine of x plus our particular solution, which happens to be this cosine of x times the logarithm of the secant of x plus the tangent of x. So again, if you like the content, please subscribe.